All right, if you're gearing up for an exam like NEET, you know that physics can be a real beast. Today, we're going to tackle one of the most fundamental topics, and honestly, one of the most confusing, kinematics. We're going to get crystal clear on the difference between distance and displacement, and what really separates speed from velocity. So let's jump right in. So, let's kick things off with a question. Picture this. Your fitness tracker is buzzing, celebrating those 10,000 steps. Awesome, right? But how far are you, really, from where you started this morning? This simple question, well, it gets right to the heart of what we're digging into today. So let's start with what I like to call a tale of two paths. This is where we unpack two ideas that sound similar but are actually worlds apart. Getting this right is absolutely the first step to mastering these kinds of problems. First up, we've got distance. Now, I want you to think of this as the scenic route. It's the total ground you covered. Every single step, every turn, every meter. It's literally the number your car's odometer adds up. It only cares about how much, not which way. That's what makes it a scalar quantity. It's just a number. And then, on the other hand, you've got displacement. This is the super direct, no-nonsense route. It completely ignores your winding path. All it cares about is the straight line from where you started to where you ended up. You know, the as the crow flies path. And because it has a length and a direction, we call it a vector. Okay, let's put these two head to head, because this is where exam questions really try to trip you up. Distance, scalar, total path, always positive. Displacement, vector, shortest path. And check this out, it can be positive, negative, or even zero. It all just depends on where you end up relative to where you began. And here is the ultimate test. The round trip. Imagine you run a full lap on a 400-meter track. You've definitely covered a distance of 400 meters, right? But because you end up exactly where you started, your displacement is a big fat zero. This is such a classic exam trap, so lock this one in your brain. All right, so we've nailed down our two paths. But what happens when we start the clock? This is where motion really comes alive, and where we meet two new friends, speed and velocity. You guessed it, speed is distance's best friend. It simply tells you how fast you're covering that total winding path. And just like distance, it's a scalar. Your car's speedometer, that measures speed. It tells you how fast, but it has no idea where to. And in the other corner, we've got velocity. And just like speed is tied to distance, velocity is tied to displacement. It's not just about how fast you're going, it's also about which direction you're headed. It's a vector. So 60 kilometers per hour is speed. 60 kilometers per hour due north, now that's velocity. Okay, listen up, because this is a golden nugget for your exams. Since displacement is always the shortest path, its length can only be less than or equal to the actual distance you traveled. That means your average velocity can never be greater than your average speed. They're only equal if you move in a perfect straight line. Okay, theory's done. Now it's time to load up your physics toolkit. These are the powerhouse formulas and shortcuts that are going to save you precious time when that exam clock is ticking. Let's break this down real quick. For average speed, it's simple. Total path over total time. For average velocity, you got to use that net displacement. And instantaneous velocity, that's just your velocity at one specific single moment in time. It's what a velocitometer would read in that exact instant. Now, this one, you are going to want to write this down. This is the secret weapon for a super common exam setup. An object goes somewhere and comes back, or covers two equal distances at different speeds. This little shortcut gives you the answer directly and saves you a ton of work. So, theory's done, toolkit's packed. You know what that means? It's time to get our hands dirty and put this stuff into practice with a couple of classic problems. Here we go, challenge number 1. A person walks 5 meters east, then 4 north, then 3 west. Notice it's asking for two totally separate things, total distance and net displacement. We have to treat them differently. Okay, don't get overwhelmed. We've got a simple 3-step game plan. First, the easy part. Add up the whole path for distance. Second, we'll figure out the net movement, how far east-west and north-south they ended up. And finally, a little high school geometry to find that final straight line path. First, let's tackle the easy one, distance. You just add everything up, right? 5 meters plus 4 meters plus 3 meters. Simple as that. The total distance traveled is 12 meters. Done. Now for the trickier part, displacement. The person went 5 meters east, but then came back 3 meters west. So net movement, that's 2 meters east. They also went 4 meters north. So now we've got a right angle triangle with sides of 2 and 4, a little Pythagoras action, and we get the square root of 20, which simplifies to 2 root 5 meters. That's our displacement. Okay, next problem. A car goes from A to B at 60 and comes back at 40. Wait a second. Does this ring a bell? It should. This is that classic there and back again scenario. It's the perfect time for our shortcut.
And bam, this is where that shortcut becomes your best friend. We just plug the numbers in. 2 times 60 times 40, all divided by 60 plus 40. That's 4,800 over 100, which gives us an average speed of 48 kilometers per hour. See? Way faster than doing it the long way.
Let's wrap up with one last really important idea to lock in. If something is moving with a uniform velocity, and that means constant speed and constant direction, then its average speed and its speed at any given moment are exactly the same. It's the simplest kind of motion, but it's a key principle.
Which leaves us with one final thought to chew on. Your speedometer shows you're doing 60 kilometers per hour. But if your car had a velocitometer, what would that be showing you? It would have to show both your speed and your direction. Never, ever forget that difference. Thanks for joining this explainer.